so the next part of this lecture is Canny edge detection. And let's quickly go over the steps we have in this edge detector. Same as like the previous algorithms, we will first smooth the image. And again, we are using Gaussian filter here. Then we are using first order derivative to find the edges. Like in Mar-Hildreth, we saw second order derivative, but again, we moved back to single order derivative. Then the next step is we find the magnitude, which again, we did for Sobel and we did for Privet as well. Now, this is something new. We will also rely on the orientation of the gradient. All right. So this we know how to compute it. Then these are additional steps we have not seen before in the prior algorithms. So orientation is the first. Then the second is non-maximum suppression. We will talk about what non-maximum suppression is. And then again, we will apply thresholding, which we have done before as well, but this is slightly different. I think a better version of thresholding. And this is called hysteresis thresholding. We'll also talk about this. Okay. So basically, the first two steps remains the same. This we have seen. So partially we know the third step as well. These three are the additional steps, and we'll go into more detail of these steps. Now, this is like, let's say your input image, and this we know is like this is like derivative, first order derivative of a Gaussian filter. Again, this is just visualization of the smooth filter, which will look something like this when you look from the top. Okay, so this is in X direction, this could be in Y direction. And again, so this is interesting, right? So filtering, we discussed this earlier as well. It's kind of pattern matching. So whatever pattern we want to see in your input image, we use the same pattern in your filter. And this you will see like over and over again, even when we talk about convolution neural networks, there also we will see that it's all about pattern matching. And so if you look at this, this is kind of going from very bright pixel to very dark pixel, right? And that's exactly what edge looks like. You go from like a very negative value to a very positive value. Your values are changing, right? Values are changing. So the filter actually looks like that. And if you're using such a filter, it means that it's trying to find pattern like this in your input data. And of course, this is like you can see the vertical edges, and this is the horizontal edges. And that's why like using these two different derivative kernels, or you can say Gaussian kernels, help you in finding edges in different directions. Okay, so these are again the same steps we have seen earlier: input image, X derivative, Y derivative on the smoother image, nothing new. And this is the magnitude. This also we have seen. So this is basically similar to your Privet edge detection or Sobel edge detection. All right, so we won't go into detail of this. This is something new. So once you have these edges, what we do is we try to find the orientation of the edges, which means like in which direction we have edges in the input image. All right. So this is just one visualization, and essentially what's happening at each pixel location, we are trying to determine in which direction the edge actually lies. We're trying to find the orientation, and you know the formula to compute that. Okay. So if you try to understand this visualization, we have actually used a color for each direction, right? Because you have like, let's say 360 different directions, and you can easily assign like one color to each direction. It could be a smooth map or something, color map or something like that, right? So if you look at this, the red color is actually looking at all the edges which are tilted towards left, right? So you can see like this is red, and these are like slightly red. This is also red, right? So all the edges in this direction. So which means that it's kind of giving a sense of in which direction the edges are actually placed in this input image. All right. And again, so that's red. And again, blue you can see is like all the edges towards the right. Now, how we get these values? So this is just color coding. So you have the orientation of each pixel, and you use the color from a dictionary or a color map and just plot that. So it's just visualization. But how you get that orientation, you know like the formula of, let's say, tan inverse fx over fy or fy over fx, right? You can just use that formula to get these orientations at each location. So that's the first step. Now, the second step is non-maximum suppression. And the idea here is what you want to do is you want to look in a local neighborhood, and for each location or each pixel in your input image, you want to say that whether the magnitude of this edge is actually greater than the neighboring pixels or not. Okay, so if the magnitude is greater than, then you say that it's an edge. So which is kind of you're saying if it's a peak or not. So if it's a peak, then this value will be higher than all the other values in the neighborhood, right? Then you say it's an edge. If it's not, you say it's not an edge, irrespective of whatever like magnitude you have. Now there is a catch. When you look into the neighborhood, you only look into the orientation of the edge. So if let's say your edge is has this orientation, right? So you will only look in this direction. For example, let's say we are interested in this pixel location Q. What we will do, and this is the direction, we will just draw this and we'll try to find the magnitude of H at the neighboring values. Okay, and we'll compare this value with this values. And if the magnitude at this location is higher than these two, R and P, we will say Q is an H. Now, sometimes it may happen because this is not a continuous space, it's a discrete space. In this orientation, you might not have any pixels. So in that case, what you will do is you will try to interpolate this value using the neighboring pixels of that location, right? So in this case, R, you will get, it could be like a weighted average of this pixel and this pixel. Similarly, P will be a weighted average of this pixel and this pixel. And then you will compare value of P and Q and Q and R. And depending upon what the result is, you will say Q is an edge or not. All right. So let's try to visualize this. If this is your edge, then orientation will give you something like this. Okay, so the orientation is not like where the edge is inclined towards, it's giving you the normal. All right. So let's make this discrete. And in this case, if these three are pixel values, x dash, y dash, xy, and x double dash, y dash. So at this location, what you will do is you will call this as an edge only if the magnitude of your first order derivative is greater than x dash, y dash, and x double dash, y double dash. Otherwise, it's not an edge. So that's like a very, very simple rule here. Okay, so it's just saying that what I explained. Okay, so let's see like how the edges will change. This is a before non-maximum suppression. And after suppression, you can see what it actually doing is it's actually thinning your edges. Okay, so if you focus on like edge of this cap over here, in the original version, you can see like it's kind of thick, but what this non-max suppression is doing is it's making it thinner. So what happened is, because this is the edge direction, so the normal will be in this direction, right? So if you look at this direction, then only one of the pixels will be called an edge. You will suppress all the others. Okay, so that's like one additional step we have in Canny edge detection. Now we have one more step which tries to use like some kind of threshold to suppress further edges, like which are not real edges. And this is called hysteresis thresholding. The idea is instead of having a single value of threshold, we have two different values. So that gives us like some kind of bandwidth. Okay, so we call these lower threshold and higher threshold. Now let's try to understand how this hysteresis thresholding works. So what we will do is, let's say the x-axis is just like different pixel locations in your image, and this is the gradient magnitude. Okay. Now let's say your low threshold is somewhere around this, the blue line, and higher threshold is somewhere around this line. Earlier, when you had just one threshold, then you just use it, and anything which is above it, you will say edge. Anything below it, you say non-edge. But this is slightly different. So there are three steps. The first is you will look at the lower threshold, and any pixel magnitude which is lower than this lower threshold, you will say that's not an edge. You will completely ignore it. Okay, so that's clear. Then you will look at the higher threshold. Then you will check the values. If the value is greater than the higher threshold, you will say it's an edge. Okay, so those two steps are pretty clear. It's standard like from the previous algorithms. The interesting part is the central region. Okay, so now the idea is, when you think about, if you visualize your edges in this image, let's say, so you can see like there is some kind of connectedness in these neighboring pixels when we are forming an edge. So for example, this edge over here, it's continuous, right? It's not that like one pixel is edge, then there is discontinuity, another is edge. We don't have that, right? So it's a continuous edge, and that's the intuition here. What we do is we try to find like those connected components in the edge map. And if there is an edge, like edge mean like all the connected pixels, if all the connected pixels are below this threshold high, we say it's not an edge. So this is kind of a weak edge. But if we find there is an edge in which like some of the pixels are actually above high and some of them are below high, so we will discount them and we will say that, okay, this still discounts as an edge. So we discount all these pixel values, pixel locations, and instead, like when they were lower than the high threshold, still we are counting them as an edge. Okay, and of course, like if the whole edge is like above this side, that's definitely an edge. And if the whole edge is like below this low, that's not an edge. Okay, so this is just, these are just the steps like which I briefly explained in the previous slide. Now, one interesting question here is when we're trying to find like the connectedness of the pixels, whether like those are neighbors or not, there are different ways to do that. We can have 4 connectedness. Like if we are looking at this pixel value, so if they are connected like in this neighboring way, like left, right, top and bottom, we say they are connected. So this is like 4 connectedness. This is 8 connectedness, and we have to do this because we have a discrete space. It's not continuous, right? And we can have like other variants, like maybe in the diagonal or in the other diagonal, which is fine. Okay. So the idea here is, let's say you have this pixel, it will have some kind of magnitude. You have this pixel, some magnitude. And if these are neighboring pixels, then you can say like they belong to the same connected component. Okay. So if you use like that hysteresis thresholding on top of non-maximum suppression, you can see like this is a much nicer result we have seen so far. Okay, much better than all the other algorithms. So this is kind of suppressing all the non-negative edges. Now, as we saw, the effect of Gaussian kernel on Mar-Hildreth, the same effect will be seen here. If this is an original image, let's say if we use a standard deviation of 1, we'll get something like this. You can see like we are still able to detect these fine level edges here. And if we increase the standard deviation, which means we are looking at a bigger neighborhood, so these fine grained edges are actually being disappearing, and we are getting like a bigger, high, like a coarse level picture. Okay. So again, it depends like what kind of edges you are interested in. If you really want to detect like these fine grained edges, use a Gaussian kernel with a small standard deviation. If you're not interested in fine grained edges, you want like just a coarse level picture, what's the like high level structure of this image, then you can use like a high standard deviation. Okay, and of course these are like traditional approaches. These days we have many like advanced deep learning algorithms to detect edges, which gives you much better performance. Even like some of the recent, and these are not recent methods. I think these should be from 2017 or 18. I don't exactly remember, but you can see like they're already matching the human level performance. Okay, later we will see like if we are fast enough to cover all the topics and we have time, we will try to touch upon this aspect, how we can detect edges using deep learning.